With this problem, we've got a three-phase 4-wire unbalanced load, and we have a neutral in the circuit, 400 volt line voltage, and we're being asked to use a phasor diagram to indicate phase voltage, line voltage, phase currents, and what the current in the neutral conductor is. So a bit of analysis first up on the circuit. We can see here we've got the line voltage there is equal to 400 volts. So therefore the phase voltage in a star connected system is V phase is equal to your V line divided by the factor of root 3. So 400 volts divided by root 3, square root of 3 gives you that 230 volt phase voltage. Therefore the currents, you can see the impedance of each phase is different, so they're going to be drawing different currents in each phase, and we're going to have an outer balance current in the three-phase system that's returning back through the neutral conductor. So the current in the A phase would be your phase voltage, A phase voltage divided by the A phase impedance. So 230 divided by 10 ohms is equal to, of course, 23 amps in the A phase. The IB phase, again, 230 divided by 8 ohms in the IB, which is equal to 28.75 amps. And the IC phase, 230 divided by 12 is equal to 19.2 amps. So we've got to use a phasor now to determine the value of neutral current. You can't just do it off the figures there. So our phase voltages we saw were 230 volts, our line voltages were 400, and the phase currents were IA at 23 amps. IB was 28.75 amps, and IC was 19.2 amps. Pretty sure? Yeah. So that's the information we've got now. There's no power factor involved at the moment with these impedances, shown as purely resistive, so we can draw them in phase with our three-phase voltage phasor. So we'll start again with a voltage reference phasor, our three-phase voltage reference, phase A, VA, representing 230 volts, 120 degrees down to the B phase, 120, and the C phase will be up there at 120 degrees, considering our direction of rotation is anti-clockwise. So draw them in. VC and VB down there at 230 volts, of course. Our line voltages are actually between these 2 points here. I'll just draw them in dotted lines so we can see where the line voltages appear. You could draw them, the line voltage leading up here by 30 degrees, doing the phasor addition to the old Mitsubishi sign that we call it, but that's the other side of the parallelogram down here, and the distance between those tips of your phase voltage is equal to the line voltage. So VL, V line, which is between A and B. Okay, same between these 2 points here, would be equal to the line voltage. So that'd be V line between B to C. And over here we can complete the triangle. We've got V line C to A. So that's our voltage phasor, basically showing phase voltages of 230 and 400 for the line voltages. Now we plot these phase currents. We'll plot them in phase with the phase voltage and work out a little scale there. So let's say we've got 28 amps is going to be our longest phasor. So if we do say 1 centimetre is equal to the current, 1 centimetre is equal, let's say 4 amps can be our scale, and hopefully we can get all that on the page. So 4 amps in the A phase is 23 divided by 4. 23 divided by 4. So 5.75 long, about 5.8. There's the A phase current. IA is 23 amps. The IB 28.75 divided by 4, so that's 7.18, 7.2 long. So 7.2 down on the B phase. Down to that point there. Okay, so that'll be IB, which was 28.75 amps, and IC was 19.2, so 19.2 divided by 4, 4.8 long for the C phase. So we go up there, 4.8. And that's IC at 19.2 amps. So I've got to add them by phasor addition now to determine the current in the neutral conductor. Okay, so you grab your compass out and take any two phasors again. Grab this two, we'll add A to C, so the length of A to C, come up to the tip of C and scribe an arc. Then we get the length of IC, come to the tip of IA and scribe that arc up there. Where the two arcs intersect is going to be the resultant of those two phasors added together. Up there at a small angle, you can see up to that point there. So now you've got to add this resultant to the value of IB. So again, we get the compass out, get the length of that resultant there, come to the tip of IB and scribe an arc, and then we get the length of IB up there, come to the tip of that resultant there and scribe an arc. And where those two arcs intersect again will be the resultant of this phasor addition. It's about at that point. It's hard to see on camera there, but it comes in at about that point there where the two arcs are intersecting. It's basically from that point to there is about 7.5, and from that point to there is about the same, so we've got the same parallelogram, if you like, which has been done between there and there, there and there. See, so about nearly 5.5 and nearly 5.5. Okay, from there to there is about 7.5, and from there to there is about 7.5. So where those two arcs intersect becomes the resultant or the value of your neutral current. So put that up there, down to that point. Oops. Just back there. And of course the direction is flowing back in to the star point. The value, we could then go to our scale, is about 2 centimetres long. So 2 times 4 is equal to about 8 amps. So the value of neutral current is 8 amps.